All right, so far so good. So we have the expression for the rate of change of the interior temperature of the NCSTR, but within this expression, we haven't really discussed, this Q dot N, right? It's just the heat the rate of change at which heat is escaping or entering the interior of the NCSTR, right? So when we actually take a look at this diagram here, it's more clear. So this is the energy balance, right? Total internal energy, and then the enthalpy associated with the n stream and n minus 1 stream. And then there's actually heat transfer from the interior to the wall of the CSTR, which we assume has finite thickness, right? And then we have another heat transfer from the ambient temperature to the wall of the CSTR, right? So there's actually this term Qn, Q dot N, is what we're looking for in terms of the energy balance for the interior temperature. And then this Q dot NW is heat exchange between the wall and the outside ambient environment. So how do we write this, heat transfer rate? Where it's very similar to the linear driving force model, but we can actually write this heat transfer coefficient times surface area of the contact area times the temperature difference across the wall and interior, and then this will give us the rate of heat exchange between the end CSTR wall and the interior, right? Similarly, you can write the expression for heat transfer between the wall and the outside of the end CSTR. So that's actually pretty simple to do. And then you can actually write the energy balance simply, right? Because there's no generation of the heat or consumption of heat within this wall of the CSTR because there's no reactions going on. So it's just the whatever comes in, whatever goes out, right? If you do that, energy balance and then simplify, you just get equation 19, with AW being some sort of lumped factor for accounting for the geometry, right? And CPW is the heat capacity of the wall.